Hello, and welcome to our 9 a.m. press conference, Future Himalayan Seismic Hazards, Insights from Earthquakes in Nepal. Our speakers this morning are Jeffrey Kargel, Senior Associate Research Scientist and Adjunct Professor, University of Arizona Department of Hydrology and Water Resources; Dan Sugar, Assistant Professor of Geoscience, University of Washington, Tacoma; Dalia Kirschbaum, Research Physical Scientist, NASA Goddard Space Flight Center; Oliver Karup, Professor of Geohazards, University of Potsdam Institute of Earth and Environmental Sciences; and Eric Fielding, Principal Scientist at NASA's Jet Propulsion Laboratory and the California Institute of Technology, is in the audience for question and answers following the presentation. Thank you.
Well, thank you very much for that introduction. And we've got the slide up. Okay, so I want to acknowledge the co-presenters here. You'll be introduced one by one as we speak. And I do want to mention that there are two papers, related papers, coming out in Science, or I guess they're out at this point. And this press briefing will be covering both of those related papers. There were some big surprises from the Nepal Gorka earthquake, and I'll focus on the surprises. The highest parts of the Himalaya actually lost elevation, while the lower mountains and basins to the south increased their elevation. There was this pattern of downdrop and uplift. Landslides occurred in a peculiar pattern, which I will describe shortly. The number of landslides was far fewer than in other similarly powerful earthquakes. Very good news, Glacial Lake sustained very little damage that we're aware of so far, contrary to the most fearful expectations that many of us held. While the earthquakes caused a huge loss of life and devastated some remote Himalayan valleys, the situation could have been far, far worse, but wasn't. Next slide shows a map of the distribution of landslides that were induced by the earthquakes. The purple dots show that. You'll also see two red circles that correspond to the primary shock of magnitude 7.8 on April 25th, 2015, and the largest aftershock, which occurred May 12th this year, magnitude 7.3, which is a large quake in its own right. You'll also see a pattern of red and blue, which corresponds to the crust and surface uplift and downdrop, which I just mentioned. Here's a spectacular photograph of Langtang Valley. This was one of the hardest hit areas of the higher Himalaya. This is a pre-earthquake image taken in 2012 by the cinematographer and one of our co-authors, David Brashears. It shows Langtang village within the Langtang Valley. There were several other villages that were also hard hit by the earthquake. Next slide, you'll see the very same vantage point in Langtang Valley. You'll see in this slide an immense landslide which covered over this village. I will toggle back and forth and you can see the differences. Very tragic, about 350 people were killed in this valley. Next slide shows Shorolpa, which is considered to be one of Nepal's most dangerous glacial lakes. You can see that it's brimful. Quite a few glacial lakes match this description of being brimful. This one is particularly hazardous in part because of the very narrow damming end moraine. These are considered very delicate structures. Many people think that they're just poised to collapse with, a little bit of shaking, and indeed many of them might be. What you see pointed out by the arrow that says lake outlet, this is an artificial outlet. You can see a building for scale, and in the next slide, you can see those buildings. This is the engineered outlet, which was constructed around 15 years ago to artificially lower the level of the lake and reduce the hazard. You'll also see some cracks. This is a photo by USGS scientist Brian Collins. 2 areas of cracks in this structure. We think that these are primarily superficial. They don't pose a big risk to the safety of people downstream from this lake, but these cracks do represent some possible earthquake-induced damage. Otherwise, there is relatively little damage observed for earthquakes. Certainly by satellite, we saw very, very little. In conclusion, 4,312 earthquake-related landslides and other induced hazards were mapped in Nepal and adjoining Tibet. There were far fewer landslides than caused by earthquakes of similar magnitude elsewhere. Some landslides, such as Langtang, were terribly tragic, as we saw evidence of. There could have been many disasters on that scale, but reduced landslide numbers helped many valleys. Very little damage to glacial lakes also helped the situation. The reasons for the reduced number of landslides is an area of ongoing research. Possibilities include very high rock strength and the earthquake's unusually gentle shaking at the surface. Damage at glacial lakes was also much less than expected, possibly due to the way that the earthquake's seismic waves interacted with the rugged topography. And with that, I'm going to turn it over to Dan Sugar.
Thanks, Jeff. So this map shows the distribution of landslides from the Gorka earthquake as mapped by the international mapping effort that we were part of. It's a similar map to what Jeff showed a few minutes ago. But what's important here is that not all of the landslides occurred during the earthquake. Many occurred in the weeks after, as I'll show you in a minute. And most, but not all, occurred at the ridge tops, which would have been more expected. Where the underlying geology allowed it, some of the landslides occurred right down in the valley bottoms, which were quite flat. And so we're going to head to this circled area here, labeled Pisang. We're going to look at a village, or right near a village called Lower Pisang, which is in the Annapurna region of the Nepal Himalaya. So the next slide is a Landsat 8 image from 4 days before the earthquake. And unlike at Langtang, as Jeff just showed, where the landslide was a combination of glacial ice and very steep bedrock, the landslides we observed in the Marchiandi River Valley were of an entirely different nature. They were initiated in the flat valley bottom sediments as opposed to the steep slopes here. And this valley experienced relatively weak shaking, especially compared to Langtang, for example. And so each of these dots represents an individual landslide that occurred in the roughly week and a half to 2 weeks after the main April 25th shock, and they're color-coded by date. And so we'll zoom in now to this white box here just upstream of the village of Lower Pisang. So the next slide shows a zoomed-in view of a high-resolution WorldView 2 satellite image. And so the April 25th earthquake triggered 9 landslides in those valley bottom sediments. And those landslides collapsed into the river, many of them forming relatively small lakes. So in this image, you can see a small landslide here, about 50 meters wide, not a huge landslide, and a small impoundment of water just upstream. The river here is flowing from top to bottom. Next slide shows a week later, a further 5 landslides occurred into this stretch of the Marchiandi River, including this considerably larger one, about 200 meters wide. And this landslide caused a much larger lake to form upstream. This lake eventually reached a volume of about 373,000 cubic meters, and that's about 150 Olympic-sized swimming pools. I know everybody wants swimming pool volumes. And in the following few days, another half dozen landslides occurred into this stretch of the river for a total of 20. And so the next slide shows the same area from late May, and what you'll see here is that this larger landslide dam is actually still intact in late May, roughly a month after the earthquake. And so this is just one of the lakes that was dammed on this stretch of the river. All told, all of the lakes on this stretch of the Marchiandi had a volume of about 640,000 cubic meters, or about 256 Olympic swimming pools. And the persistence or the stability of this dam, this larger one, was especially concerning as we went into the monsoon season, which was just about a month later, because a catastrophic breach, an outburst flood from this lake here would have destroyed the village, or could have destroyed the village of Lower Pisang, which is just out of the frame here, about 2 kilometers downstream. So it's important to note that over this month period, no significant aftershocks occurred in this area, and no significant rainfall was observed. These failures were all in relatively flat valley bottom sediments, as opposed to the steep bedrock ridges at Langtang, for example, that Jeff showed. And so here the earthquake initially jolted the sediments, shook them up, preconditioning them to failure at some point down the road. But this larger landslide, for example, was not triggered during the earthquake itself. And so the next slide shows a ground level photograph, and the international mapping effort that you'll hear a little bit more about from Dahlia in a minute was helped in no small part by local villagers such as Mukia Gotame, who took this photograph. And he's a villager from Manang village, which is just 20 kilometers or so upstream. And he hiked down to this landslide dam, and the next slide will show outlined in red, that large landslide into the river here. He hiked down and sent back this great photograph, which helped us analyze both the type of landslide that occurred into the river here, but also, and perhaps more importantly, the potential threat that it posed to villagers downstream. And with that, I'll pass it on to Dahlia Kirschbaum.
Okay, we're going to go backwards in time. Can we go backwards? Thanks. Okay. Well, thank you very much. So I'd like to take a step back, and we've heard about this international mapping effort, but I'd like to talk a little bit about that and the role it played in this effort. So this global effort, this geohazard mapping team, represents one of the broadest and probably fastest analysis efforts for an earthquake-affected region that NASA's ever seen, and I think it's pretty tremendous in its own right. Now, what this was this tireless group of volunteers from about 9 nations around the world, shown in the flags below, contributed to mapping geohazards, led by Jeff at the University of Arizona, but also coordinated through this NASA-led response effort, coordinating with other, both domestic agencies as well as international agencies. And so as we described, you can see here, and zoomed in as well, there was about 4,312 landslides mapped by this team in about 6 weeks between the initial earthquake and the start of the monsoon season. Now, an important note here, and a really, so here's a zoomed in image in the next slide of some of the more populated areas in terms of high landslide density. One of the important points, if you go to the next slide, is the value and use of imagery, both optical imagery as well as radar, in mapping this collection of landslides. And so this was extremely important. Without access to this data by different space agencies as well as commercial entities providing open data for this effort, it would not have been possible. I think another important point here is that information sharing and the flow of information was really tremendous and almost unprecedented between groups like NASA, as well as the U.S. Geological Survey, the British Geological Survey, as well as science organizations in Nepal, such as the International Center for Integrated Mountain Development, or ICIMOD. Now, what happened was we would meet and we would actually have conversations about what was happening with landslides, or such as Dan described, the Pazang potential for issues in the future. And so this information was used by ICIMAD, as well as other information, to brief the Prime Minister and his cabinet in Nepal. And that in turn led to the mobilization of a geohazards task force of local geologists and other engineers to go and look at and investigate different areas in Nepal where there might be potential damage. And I think the other important point is the role of Earth observation imagery, not just optical and radar, but other information in understanding where and when landslides were happening. So what you see here in this next slide is a visualization of rainfall-triggered landslides in this region for about 7.5 years, collected from a group at NASA and myself. And the point is, as Dan mentioned, this this earthquake and subsequent landslides happened right before the monsoon season. So a huge concern going into the monsoon season was if there was going to be additional landslides mobilized because of this initial destabilization. And so one of the points here is that other information, such as rainfall information from the Global Precipitation Measurement Mission, topography data, soil moisture, and other satellite assets and modeled products, are very important for both understanding the situation for what was happening in Nepal at the time, as well as subsequent potential susceptibility and vulnerability to understand not only where landslides will be triggered in Nepal, but also around the world. So with that, I would like to introduce Oliver, who is going to describe the other paper presented in Science Today, published in Science Today, on his new findings on the legacy of large earthquakes in Nepal. So with that, I will turn it over to Oliver. Where are you? Thanks. Cool. You can do it.
Yeah. Good morning. In the paper that's going to appear in Science Today, we look at the legacy of medieval earthquakes, and we offer a long-term perspective for the 2015 Gorka earthquake. The big surprise of our study was that Pokhara, which is Nepal's second largest city and really right over the hill from the photos that Dan was showing a minute ago, that the whole city is essentially built on quake debris from at least 3 large medieval earthquakes that hit the central Himalayas. On the next slide, you can see what also really stunned us about this earthquake debris. Most of it came from a high-lying mountain basin in the Annapurna Massif, about 3,000 meters above sea level. The debris spread out over nearly 150 square kilometers and invaded several river valleys upstream against the flow direction for up to 7 kilometers. I'm not offering Olympic swimming pools here, but downtown San Francisco area would be buried beneath at least 50 meters of debris. The material forms a huge fan that is essentially plugging off at least dozens of river valleys, forming a lot of lakes. And many of these lakes exist today in the landscape and make up the high tourist attraction potential of the Pokhara landscape. On this next slide, you can see how the material has really buried many of these river valleys beneath tens of meters of sediment. And on this slide, you can see that this material is quite varied, and leaves and remnants of old wood and charcoal that we pulled out and dated show that these layers were more or less formed during 3 distinct pulses around 1100, 1255, and 1344 AD. And these are the dates of well-documented large Himalayan earthquakes. Now, doing the fieldology on these deposits, as we do as field scientists, we find that the composition of those sediments rule out any local source. Okay, so this is completely different what we experienced in the Gorka earthquake. The material is not coming or derived from the nearby hill slopes. Rather, it comes from a source about 60 kilometers away, and the material itself and its makeup is consistent with several catastrophic lake outburst floods. So how does this fit the big picture? What are we learning from our study? Well, for one, we have this unique sedimentary archive, okay? It's like a book that is enabling us to now validate independently the timing of large Himalayan earthquakes and possibly even detect new events that other studies have not found so far. And the second outcome is really now that we can also trace the landscape changing impacts of these large Himalayan earthquakes, okay, that are pretty much unparalleled as far as we know at this stage. So are we done yet? No, the final surprise really was that the rivers keep on adjusting to this high amount of debris that's been flushed into the valleys. So they incise, okay, they shift their courses, they undermine the banks, there's sinkhole collapse problems, many centuries after the original seismic disturbance. So on this final slide, to wrap things up of the contributions of both papers, the 2015 Gorka earthquakes this year triggered fewer landslides than we really had expected, okay? Many of the glacial lakes were remarkably resilient. However, more and more landslides occurred after the main shock, okay? And free and open satellite imagery was really key and indispensable for documenting and analyzing the earthquake deformation as well as the regional landslide impacts. And having a detailed look back in time really pays off well. So the Pokhara landscape is suggesting that larger Himalayan earthquakes centuries ago could have triggered far worse impacts on the landscapes. And with that, I thank you very much and pop up with the contacts. Thank you.
Thank you. We'll now open the floor for questions. Just a reminder that only registered reporters may ask questions. If you could please state your name and affiliation.
Hi, I'm Tia Ghosh from Live Science. Sorry, I have a little bit of a tickle in my throat. So I'm just wondering if those medieval earthquakes, if we have any estimates on their magnitude and where their epicenter was located.
Does this work?
Mm-hmm.
Thanks for that question. There's ongoing studies about the magnitude and the locations of those earthquakes. Most of the information that scientists take from this is from fault trenches, okay? So they dig trenches across those fault lines and they date the various layers that are being offset by the fault rupture. The exact magnitudes are about 8 or larger, but it's pretty difficult actually to constrain them much better. And there's quite some mysteries about which sections of those faults ruptured during medieval times. So it's still an ongoing puzzle. Does that answer your question? Okay.
Yeah, Jonathan Amos, BBC News. Kind of a two-part question, I guess.
We
here.
can't
Sorry, yeah. I shall speak a bit louder. Kind of a two-part question here. The first is, can you explain the mechanism for why the landslides are where they are on that northern part of the fault, the bit that went down? And then can you just update us on what's happened after the study, i.e. the monsoon? I mean, obviously the ground has experienced this trauma. It'll take a while, several years for that ground to recover. In the meantime, monsoons are going through. So, what's happened after the study? Period.
For the first question, I can answer the second question, but maybe first Eric Fielding could provide an answer, since that's sort of a geophysical type question, and he's a geophysicist.
And one of the co-authors of the first paper.
Yes, yeah.
Yes, it's Eric Fielding, JPL. The landslides are largely in the areas of steeper slopes, as expected. And that area of steeper slopes was also the area that where the ground moved downward during this earthquake. Over geologic time, we know that area is uplifted because there's high mountains there. But during this earthquake, that part moved downward, and it seems to have triggered the landslides in that area. And it's very clear from the radar imagery that the spatial extent east-west is of the landslides is directly correlated with the fault slip at depth.
Are there any other questions from reporters in the room?
Then regarding the first question,
Second question.
Yeah.
okay, the first part of the second question, what we're doing regarding post June 10th, when the monsoon began in parts of the region. We cut off our observations at June 10th when the monsoon hit specifically because we wanted this paper to cover just the near-term post-seismic and co-seismic influences, and didn't want to mix it with rainfall-induced landslides. But yeah, your question is a good one, because a lot of the rainfall-related landslides are working on terrain that was destabilized by the earthquake. And in fact, we do see some evidence of that. And I visited in October, November, I visited several landslides that were induced. Some of them were induced directly by the earthquake on April 25th, and others were triggered on June 10th when the first heavy monsoon storm hit. And we have to take a detailed geological approach and a statistical approach to really figure out whether the earthquake had anything to do with those, or whether they were just independent rainfall-related events. I think there might also have been additional causes responsible for the down-drop uplift pattern, but it's an area of ongoing research. One additional mechanism that might have come to play is literally the alleviating of stress due to the weighing down of the rocks on slip planes, fracture planes, when the crust dropped down. But unraveling the causes of that pattern is a complicated thing, because so many different processes are at play simultaneously.
Yeah, hi, Doug Prose with Earth Images Foundation. And given that the segment of the main Himalayan thrust fault in the Pokhara region is sort of thought of as maybe the location of a future quake, maybe more so than any of the other segments in that region, how does the landslide threat add to the just general earthquake threat there? And is there potential for future quakes in that region, given that there's already been some pretty huge landslides already?
I think that's either another Eric Fielding question, or Ken Hudnut from USGS is also in the audience, and so both of them may have something to say about this.
Yeah, we know that this earthquake did not release all of the stress that's built up on the main Himalayan thrust, and so there's certainly a clear danger of future earthquakes that could cause more extensive landslide damage, as shown by the paleo landslide mapping that Oliver talked about. Clearly in the past there have been larger events that produce more damage and much greater landslide. So I think we do have to consider that there is a significant risk of future events.
Yes, my name is Ken Hudnut. I'm with the U.S. Geological Survey. So we call that question the what's next question, and it's unfortunately something that we're not able to predict accurately. You know, there's heightened level of concern after any significant earthquake of the possibility of damaging aftershocks. Christchurch, New Zealand springs to mind as an example. But after the earthquake in Haiti, we were also asked to provide any insight about what might occur next. And so this is a common concern. It arose again after this major damaging earthquake, of course, and we were asked by embassy staff, in particular Ari Nathan with the State Department and the Kathmandu Embassy, this what's next question. And so although it's a very pressing, important question, it's not one that we can exactly answer. What we have done, of course, is monitor for aftershocks along with NSET and in-country colleagues that operate the seismic network there. Caltech has a GPS network that was used in the months after the earthquake to see what the post-seismic deformation was like. And I can say on behalf of Professor Jean-Philippe Avouac from Caltech that processing of the GPS data shows that, like the aftershocks have been occurring more or less within expectations, and the post-seismic deformation, I would say, similarly is within expectations. It's not like there's some runaway process occurring that's showing up in aftershocks and geodetic data. It's more like, well, this is all falling within expectations. But also I should say that it is well understood that there is geodetic evidence for strain accumulation throughout the Himalaya and also evidence for early historical earthquakes over in that area. So heightened concern is still a reasonable feeling and anticipation, but with a lot of uncertainty. Who knows what might happen next? Unfortunately, we can't be precise in any answers on that. Good question.
Thank you, Ken and Eric. I want to point out that Ken is another one of the authors on the paper.
I just wanted to add a comment about the specific landslide hazard going forward on that sort of western side of the area that we were mapping. As I said, it was sort of the western extremity that we saw very many landslides occurring, and there weren't any large aftershocks that far west near Pokhara. But every earthquake is going to destabilize slopes going forward, precondition them for later failure. And Professor Dave Petley, who's in the audience, just published a paper recently discussing this exact issue. So should, in the future, another large earthquake occur along that segment of the fault further west, one would certainly expect landslides there to be quite significant.
Yeah, Rick Lovett, freelance. So I'm interested in the vertical motions. How much did it move down in the areas where the landslides occurred? And as long as we're asking that question, how much did the high elevations, how much did it change in those areas? And how much did the high elevations go down? I mean, Everest is now shorter. By how much?
I used the radar imagery to measure the vertical motion, and the area of Everest is actually well to the east of the area that was affected by this earthquake, so it had basically no motion. But the area just north of Kathmandu moved upward by about 1.5 meters, and the area further north into the high Himalayas there moved downward by about 1.4 meters. So the amount of downdrop was a little bit less than the amount of uplift during this earthquake due to the configuration of the fault at depth. And the whole area also moved southward by about 2.2 meters. So the southward motion is larger than the vertical motion.
And just to add to the points made about Everest, yeah, it was at the very fringe of the earthquake deformation zone, but it was not shaken very much, but it was shaken. And in fact, those of you in the media probably remember that one of the first disaster stories within this bigger earthquake disaster story were the Everest ice avalanches, which killed quite a few people in Everest's single deadliest day on record, the previous record having been just last year. And so the amount of shaking was enough to destabilize ice that was hanging on the cliff sides, just ready to collapse anyway, most likely, especially as spring melting was starting to get underway.
I think we have a question on the chat.
This question is from Sarah Hammond from Arizona Public Media. This is for Jeff. Could you please talk about what role your team's efforts played in the emergency response and recovery from the April earthquake and future preparedness efforts?
That's a good question. I'll let Dahlia speak to that after I just make some brief comments about it. So the part of the value of our effort was just seeing that we can organize in a big team, interdisciplinary team, get a lot of eyes and minds on the data and extract meaningful information in almost real time, enough to assist people on the ground. And so I think that was one of the key things. So, we can always do things better next time, and, we'll aim to do so. I think in terms of organizing a satellite campaign, this has been done many times by NASA, but as Dahlia mentioned, it was fairly unprecedented in scale in terms of the number of satellites involved. Of course, we have a lot more satellites up in space now than in previous years, and the interaction with different agencies in the U.S. government and with, as Dahlia mentioned, in academia. So yeah, the organizational part of it is one valuable lesson. We can always do things better, but we're happy with what we did do to help. The other aspect is in terms of the science of this, the understanding of the earthquake's effects on the landscape. And each time a disaster happens, there's tragedy, of course, but there's also a lot of knowledge that's gained, a lot of understanding. And sometimes it's not always in the direction of making predictions ever clearer and sharper. This earthquake had a lot of surprises for us, and it sort of opens our eyes to other complicating processes and the many parameters that go into determining what a particular earthquake's effects on the landscape will be. In terms of the organization of this, Dahlia gave a great presentation, and I don't know if you want to add anything.
Well, just that there was an outpouring from everywhere, international agencies, aid organizations for this earthquake. And our role really in this was providing satellite imagery and scientific expertise to aid those that were doing the on-the-ground response. And I think it's important to note the recovery effort is still ongoing, and it will be for a long time. So it's important, I think, in this international collaboration to demonstrate what science can contribute to those that are actually responding on the ground.
Jonathan Amos again. I wonder if you could talk about Langtang. When I read the paper, the numbers in there are extraordinary. The description you give about what happened at that location is probably worth you describing here in this press conference, because it's to have been on the ground there, even from some distance away, would have just been extraordinary. So I wonder if you could do that, relate some of the numbers. People might not have read the paper in detail and seen some of those numbers, but that event just sounded incredible.
First, I have not been on the ground in Langtang, but some of the co-authors, and Brian Collins is from USGS, is in the audience somewhere here, and he has flown over that area. I don't know if you landed, but Brian obtained quite a few amazing images, as did David Brashears, whose photos I showed. In terms of the numbers, there's still rough numbers because I had to sort of guesstimate the thickness and the total volume of the landslide, of the main landslide there. There were several in the valley, but that big one that I showed went into practically a free fall. In fact, part of it was literally in free fall. And the energy involved was roughly half that of the Hiroshima nuclear explosion, or more, if I underestimated the thickness of the landslide. it was a tremendous amount of energy released. And in fact, areas that weren't even directly impacted by the landslide were very heavily affected. There's I didn't show the picture, it is in the paper, but not in this presentation. There is a part of Langtang village, let's say half of it or a big piece of it, that was literally blown away, not buried, but blown away by the landslide or avalanche winds that were set up as this tremendous mass of material went into free fall and carried a lot of air with it, and ground up snow and ground up ice and rock. And it literally blew that part of the village completely away. And we're talking about stone slab hotels, pretty sturdy structures, really amazing and horrific. And maybe, Brian, do you want to give your impressions?
While Brian's getting the microphone, I just want to add quite a few of the co-authors on the first science paper, the Gorka paper, are scientists with ICIMOD in Nepal who are intimately familiar with the Langtang Valley and were able to really provide some local expertise there. Many of the photographs that we got from David Brashears, for example, showed this air blast, as Jeff mentioned, knocking down trees on the opposing slope, hundreds of meters up the slope, just like matchsticks. So the entire forest on the opposing slope is just fallen down, not because it was buried by debris, but because of the air blast from the landslide or landslides. Brian?
Yeah, Brian Collins, USGS. I was part of a USAID mission to Nepal, and we used a lot of the data that was coming out of this study, as Jeff mentioned, in basically real time. So I was in communication.
Can you speak up a little bit?
Yep, I was in communication with them when in Nepal. So when they were finding landslides in the satellite imagery, I would get email or talk to people over the phone, and we would be able to go and visit these places the next day. We spent 5 days flying about 3,200 kilometers in a helicopter to access all these different regions, and the purpose of that was to do landslide hazard assessments. It was also, as part of that, we were able to verify the landslide inventory that the satellite mappers were getting. In terms of Langtang, we did fly the entire source area. We landed on the deposit, and we did witness a lot of the things that Jeff and Dan just discussed. The landslide started off as a ice and snow avalanche somewhere above 5,000 meters, and then slid, looking at a report that we generated here, over 1,000 meters, and then fell off of a cliff and went into free fall for about 500 meters. And that free fall was really the damaging aspect of it. It had collected a lot of debris as it slid down past its source zone, and then landed directly on the village, and the air blast radiated out about 1 kilometer in every direction from that. So not only was the village buried, but adjacent areas were also essentially destroyed by this air blast. So we saw structures made out of large stones just completely blown over. There was nothing left. And this radial pattern of tree damage, about 1 kilometer in radius, all the trees were blown off in a radial pattern from that air blast. So just a completely devastating event. We estimated the volume as around, I think, 2 million cubic meters, somewhere around there. If you compare that to other earthquakes, similar magnitude earthquakes with big events like that, it's actually fairly small according to the historic record. But that sort of goes along with what's been found out about the landslide inventory. It's smaller than what we would expect from this magnitude earthquake. That said, anytime a landslide lands on a village like this, you get devastating effects.
Are there any other questions? Are there any other questions on the chat? No? Okay, thank you. That concludes our press conference. Our next press conference is at 10:30, The New Science of Fog. Thank you.